This is the first day video for Math571, Math671, Logic 320, and Fill 412. I usually call this just Math571, and I'll probably just say that, but it has all these numbers. The basic administrative stuff is that we have a course website, www.math.upenn.edu/tilde H. Tausner, my last name, /Math571. And everything important for the course will be posted there. There's no printed textbook. There are going to be course notes, more about the course notes later, but they're posted on the website. I'll have office hours, Tuesday afternoons from 2 to 3, and Wednesday afternoons from 12:30 to 2. That means during those times, I will always be in my office. My office is DRL 4N51. I might step out to get a cup of coffee or something, and I'll put a sign on the door when I do that, and I'll be back within a couple of minutes. If you want to talk to me and you can't make those office hours, we can schedule other times to meet as well. And also, I'm in my office at many other times. And if I don't want to be interrupted, I close my door. So if you walk by my door and it's open and you have a question, you should feel free to just come in and ask. The work for the course will be homeworks every 2 weeks. They'll be assigned on a Thursday and due 2 Thursdays later. There's no exam. I really don't think that any of the material suits itself to being studied under time pressure. Relatedly, the reason you have 2 weeks is that I expect that some of the problems will really call for having enough time to try them and not be able to solve them, have to walk away and think about it for a while, and then have a few days and come back and really try to solve them. Last time I taught 571, a couple people were not prepared for this. So if you're someone who has trouble starting an assignment well before it's due, here's what I recommend. For that middle Thursday, 1 week after the assignment, expect to write down for every problem what you've done, and you should have something to say for every problem. You should have started every problem. For some of them, maybe you've written down a solution, and for other ones, you've gotten stuck. And if you need the motivation of a deadline, treat that like the assignment. Sometime in that first week, you should be trying every problem, looking at it and making sure you can solve it, so that you have that second week to think about and kind of letting ideas form for the ones that are more difficult. I have office hours on Wednesday, so if you can get that done by Wednesday, then of course you can come and talk to me and ask questions then. This is a topics in logic course. So every year we cover something in logic, but it's a different topic every year. People can repeat the course for credit. This year's topic is going to be about what we might call applications of logic to probabilistic graph theory. And I'll say a lot more about what that means later in the video. We obviously need a bunch of logic. So we'll also be talking about graph theory, and we'll need a bunch of stuff from probability theory and real analysis as well. That's a lot, and we're not going to assume you've seen any of it before. Officially, I'm not treating this class as having any prerequisite, not even Math570. I'm not assuming that you've seen any logic before this course. But we do need a lot of ideas from various areas, so we'll often introduce ideas and techniques pretty quickly. If you've seen them before, it's a refresher. But if you haven't, we might not spend enough time on some of these topics for you to really grasp them starting from zero. So you might have to come talk to me or do some extra reading to get up to speed on those. There's a lot of background material. No one in the class has seen all of it. So when we breeze through a topic and it feels like we went too fast, really do come talk to me. We'll figure out how to get you over that hurdle and keep you caught up with the class. This is a proof-oriented mathematics course. The assumption is that everyone taking it is comfortable with reading and writing mathematical proofs, including some that will be fairly complicated or long. I'm pretty skeptical of the value of me copying proofs step by step onto the board. I don't think people learn a lot by watching someone else list formal steps. When we cover proofs, especially important ones, I'm going to focus on the outline, on what the steps mean, on what the most important steps are, on the motivation, on things like why at an abstract level the proof is correct, or how the proof was discovered. The expectation is that you go home and you read the proof step by step, having seen this outline, having some guidance, but you read it step by step to really understand it. In particular, To take this course, you should be able to read a proof step by step on your own and figure out most of the steps. Sometimes there might be a step you're confused by or a step you can't follow, and then you should ask me. You don't need to understand every single step the first time you read it. The skill you need is to be able to self-assess whether or not you understand it. You can't just be reading it and going, yeah, that seems good. This course sits at an odd place in our curriculum because we only offer 2 formal logic courses a year, and so this course really has to serve 2 goals at once. This is an upper-level undergraduate course that is, among other things, the capstone course for the logic major. This is also a graduate-level course that is taken by people doing a PhD, including a PhD in logic, because this is the only graduate-level graduate-level mathematical logic course that we teach at Penn. That means I really need your feedback about how fast we're going. If we're going way too fast, please let me know. If we're going way too slow, let me know. It also means sometimes I'll ask you to bear with me because parts of the class may not be for everyone, and I'll try to make clear what's going on. But sometimes I may belabor things or go over introductory stuff at a level that's complete repetition, and please sit with that because there are other people who need it. Sometimes there are things I want to cover, and I realize we can't give all the background we need to get everyone caught up with it. So when we do that, I'll try to indicate it clearly so you know, okay, it's okay not to follow all this. But again, please try to get what you can out of that and understand that it's for the benefit of some of the other people in the class. In general, if you don't understand something we're doing, and it isn't one of those topics, so it's not something I've said, oh, this is really advanced and not everyone will get it, you should be understanding it in the normal way you understand a math class, where things are hard and you have to go think about them and struggle with them, but eventually understand them. So if that's not happening, come talk to me. I may need to slow down. We're going to have to figure out how to pace this class appropriately. And we may need to supplement a little outside of the class, either with extra reading or some extra discussion. Like a lot of math, this class is very cumulative. So once you start falling behind, it's going to get harder and harder to catch up, so don't let that happen. Finally, the class notes. Our class notes are a text that I'm writing that I hope will one day be a book. When I was a student, it was sort of a red flag when a professor used their own textbook for a course, but nonetheless, that's what we're doing. There are some other books or articles that overlap bits of what we're doing, and I'll point you to some of them along the way. But the reason I'm writing a book is that there really isn't another source. What we're covering is fairly recent, almost all of it from the last 15 years. The ideas are scattered across a lot of papers that typically don't say things in the cleanest way because the ideas were being developed as these papers were being written. The goal here is to put down the modern understanding in a unified way, and no one's done that, so there aren't a lot of other great sources. Okay, enough meta stuff about the organization of the course. What is this class actually about? I want to circle around to that by explaining a theorem called Semiretti's theorem, since one of the organizing ideas of this semester will be giving a proof of Semiretti's theorem. First, some background. There's a theorem called van der Waals theorem, which was proven in the 1920s, and it says the following. Pick a number k. Suppose I take the interval of numbers 1, 2, 3 up to n for some large number n, and I divide this interval into r sets, a1, a2, up to ar. We sometimes call this a coloring. The idea is that to each natural number from 1 to n, we've assigned a color, where the color is a number from 1 to r. So you could call a1 the red numbers and a2 the blue numbers, and so on. Van der Waals theorem says there's some bound w of rk, which depends on r and k, but doesn't depend on n, so that once n is bigger than w of rk, one of the sets ai must contain an arithmetic progression of length k. An arithmetic progression is a sequence b plus d, b plus 2d, b plus 3d, etc., up to b plus k minus 1d. So that's saying there's an I less than or equal to r, there's a b, and there's a d, so that b plus d, etc., up to b plus k minus 1d all belong to ai. The idea is that an arithmetic progression is like a pattern. And van der Waals' theorem is saying as long as you start with a large enough interval, as long as n is greater than w of rk, one of the pieces must contain a pattern. Van der Waals' theorem is an early result in an area that became known as Ramsey theory, and the basic theme of Ramsey theory is that you take a mathematical object, like a set of numbers, you break it into several pieces, and one of those pieces must have a pattern in it. Sometimes this has the slogan, complete disorder is impossible. There was a big issue people didn't like about van der Waals' original proof. The number w of rk given by his proof is very, very large. In fact, the number calculated in the original proof is on the order of what's called the Ackermann function. The details of the Ackermann function aren't important to us. They're an interesting subject, you can look it up. But for example, once k is at least 4, the Ackermann function of k is much larger than 2 to the 2 to the 2 to the 2 k times. So the Ackermann function grows much faster than the usual functions that we see in mathematics. People wanted a new proof with more reasonable bounds on how big this number w of rk can be. In the late 30s, Erdos and Turan had the idea that we could get better bounds if, instead of asking about the sets A1 through AR as a partition, we identified which of the sets should contain the partition. And of course, the answer is the biggest set should contain the structure, but there are lots of different notions for what it could mean for a set of integers to be big. So what they conjectured is that the relevant notion of bigness is density. So they conjectured that for every epsilon greater than 0, there's a bound s of epsilon k, so whenever n is at least s of epsilon k, and a is a subset of the interval 1 through n, with density at least epsilon, so the size of the set A is at least epsilon times n, then A should be a set containing an arithmetic progression of length k. So the idea is we don't have to look at this whole partition, we can just look at a property of an individual set, and if this set is big enough, then it contains an arithmetic progression. And if we have a partition into R sets, we can take epsilon less than 1 over R, because one of these sets must have density at least 1 over R. It took about 40 years for this to be proven. It was proven in the 1970s by Semiretti, and it's now known as Semiretti's theorem. Semiretti got the Abel Prize a few years ago. Of course, the Abel Prize is given for a large body of work, but the proof of Semiretti's theorem and the techniques developed in the process were one of the big components in that. Semiretti's theorem actually uses van der Waals' theorem as an intermediate step, so it doesn't help get better bounds on w of rk. Semiretti's proof introduced the idea of turning this into a question about graphs and more generally hypergraphs. For illustration, let's focus on the case where k equals 3. So we're looking for an arithmetic progression of length 3. So that's a progression b plus d, b plus 2d. Suppose we have an interval 1 through n, and we have a subset A, and A is dense. The cardinality of A divided by n is at least epsilon. Semiretti's idea was to turn this into a tripartite graph, a graph with 3 parts, x, y, and z, and all the edges are between 2 different parts. In Semiretti's graph, each of these 3 parts is just a copy of the interval, but there are rules for which edges we put in. The rule is we place an edge little x, little y between the sets big X, big Y if little x plus 2 times little y belongs to A. We place an edge between big X and big Z if 2 times little z minus little x is in A, and we put an edge between big Y and big Z if little z plus little y belongs to A. These look really arbitrary. Why these particular numbers? The idea is, suppose little x, little y, little z is a triangle in this graph. That is, little x is in big X, little y is in big Y, little z is in big Z, and all 3 edges are present. That means x plus 2y is in A, 2z minus x is in A, and z plus y is in A. And what we do is we set b equals x plus 2y, and d equals z minus x plus y, and we notice that b is x plus 2y, which is in A, b plus d is z plus y, which is in A, and b plus 2d is 2z minus x, which is also an A. So whenever we have a triangle, the progression b plus d, b plus 2d is an arithmetic progression of length 3, and it's in A. So Semiretti's idea was that if we want to find arithmetic progressions, we could instead find triangles in this graph. There's a small catch, which is that not quite any triangle will do. Whenever x plus 2y belongs to A, that gives a triangle x, y, x plus y, which corresponds to the fake arithmetic progression x plus 2y, x plus 2y, x plus 2y. So it's not quite enough to find just one triangle. What we need to do is find lots of triangles so that we know there's at least one triangle which isn't trivial, which isn't one of these x plus 2y's. We need at least one triangle which corresponds to an arithmetic progression where d is greater than 0. There are 3 times n total vertices in this graph. A triangle is 3 vertices, 1 from each part. So there are n cubed possible triangles. And what we ultimately show is that we actually have a positive fraction of all the possible triangles. The number of triangles divided by n cubed is at least delta. And in particular, that means when n is sufficiently big, there's at least one triangle corresponding to a genuine arithmetic progression. This is where probabilistic combinatorics is going to come into this class. We're going to look at densities of sets in graphs. If you've seen a typical introduction to graph theory, for example, if you took Math571 with me last semester, you've seen a lot of medium-sized graphs with small sets of edges, things we could draw on the board without lots of lines crossing. And we ask questions like, is the graph connected? Is there an Euler cycle? And so on. Here we're interested in pretty large graphs, graphs with at least hundreds of vertices, and where there are lots of edges, where the number of edges is a positive fraction of the number of possible edges. So if a graph has 100 vertices, it has 4950 possible edges, and we're interested in graphs that have at least a tenth of them, or at least epsilon times that, so maybe at least 495 edges. These are not graphs we can draw in a meaningful way, so instead we're going to look to probability theory for ideas to work with them. And the questions we're going to ask about them are things like, are there a dense number of triangles, and especially, what would it look like if this graph were random? So this is part of what we'll jump into next week, introducing the kinds of graphs we want to talk about in more detail, what kind of questions we want to ask about them, and what the tools for investigating them are. The second proof of Semiretti's theorem was by Furstenberg, just a few years after Semiretti, and Furstenberg's an ergodic theorist. So how does ergodic theory come into the story? Furstenberg gave a proof by contradiction. Suppose Semiretti's theorem were false. What would that mean? That would mean for some epsilon greater than 0 and some k, and for every bound s, we can find an ns bigger than s and a subset as of the interval 1 through ns, so that the cardinality of as is at least epsilon times ns, but as does not contain an arithmetic progression of length k. And Furstenberg's idea was to take this sequence of hypothetical counterexamples and find a limit. Furstenberg invented a technique called the Furstenberg correspondence that identifies the limit of this sequence of sets with a dynamical system. We're not going to deal with ergodic theory and dynamical systems this semester. Instead, we're going to use a more general technique that encompasses Furstenberg's idea called the ultraproduct. The ultraproduct is a tool for model theory that is going to give us a way to take a sequence of bigger and bigger graphs and turn them into a single infinite object. It will be a graph, but it will have additional properties as well. And the ultraproduct and how to build it and what properties it has and how to work with it is going to be one of the main topics in the course. That's where logic is going to come into the story. Figuring out how to take limits of graphs and what they mean, and investigating the properties of the ultraproduct, and finally using what we learn about the ultraproduct to figure out things about the finite graphs we started with. The ultraproduct is maybe one of the most influential techniques in logic. It shows up in applications to algebraic geometry, applications to functional analysis. We're going to focus on applications to combinatorics, but we'll build up general tools that are applicable in other areas as well. There are now many proofs, maybe a couple dozen, published proofs of Semiretti's theorem. But the most important one I haven't mentioned yet is Gower's proof from 1998. All proofs of Semreti's theorem, in some form, use the following idea. If the set A were random, it should be easy to find an arithmetic progression in A. Suppose A were generated by flipping a weighted coin. So we flip a coin that's heads with probability epsilon, and when it comes up heads, we put a number into A, and when it comes up tails, we don't put it into A. Then it's pretty likely you'd get an arithmetic progression. In fact, you'd probably get an arithmetic progression where D was 1. If you take any element B, and you look at the elements B, B plus 1, and B plus 2, there's some probability epsilon that B belongs to A. There's some probability epsilon that B plus 1 belongs to A, and probability epsilon that B plus 2 belongs to A. And since A was made by flipping coins, these are independent. So the probability is epsilon cubed that the arithmetic progression belongs to A. So epsilon cubed might be a small number, but if you started with a big interval, you had lots and lots of opportunities to get an arithmetic progression, B, B plus 1, B plus 2. So if A were truly random, you'd really expect to find a short arithmetic progression. So what every proof of Semreti's theorem does, in some fashion, is argue that if you don't find arithmetic progressions easily, then A must be non-random. And since it's non-random, it has some kind of pattern in it, and after a lot of work, you exploit those patterns to find an arithmetic progression. One of the ways different proofs vary is they use different notions of randomness, and those correspond to different notions of non-randomness and different kinds of patterns. Gower's big invention was to find a new notion of structure and randomness that are really the right ones for Semreti's theorem, and furthermore have some influence beyond that. In particular, they're connected to Fourier analysis in a way that we mostly won't go on, but is interesting to know in its own right. Incidentally, we're also not going to spend a lot of time calculating bounds in this class, but Gower's proof finally resolved that original concern about the bounds in van der Waals theorem. Gower's proof shows that W of Rk is bounded by 2 to the 2 to the r to the 2 to the 2 to the k plus 9, which is not exactly a small number, but it's a lot better than a tower of powers of 2 of height k. So Gower's finally gave more reasonable bounds on van der Waals theorem. The third main topic of this course is going to be this notion of randomness. We'll be focusing on the context of graphs and hypergraphs. So we'll develop a theory of random graphs. We'll discover that in hypergraphs, which you may not have seen before, so we'll introduce hypergraphs, and we'll discover there are many kinds of randomness in hypergraphs. And the tool Gower's invented, the Gower's uniformity semi-norms, will play an essential role in developing this. And that's our plan for the course. Next week, we'll jump in with Chapter 2 from the course notes. Chapter 1 is an introduction. It covers basically what I just said in this video. So in Chapter 2, we'll start talking about large finite graphs and start talking about what a random finite graph would be.